The first thing I'm going to talk about here is how we figure out sample sizes to meet an appropriate margin of error. So this is when I was talking in class about there's going to be a time to round or it's a time to round. So what I'm going to do is I'm going to go ahead and kind of walk through a couple problems and give you an idea of how to do this. So we have a problem here that says Edgar Martinez and Ingrid Gustafson are the candidates for mayor in a large city. We want to estimate the proportion P of all registered voters in the city who plan to vote. For Gustafson with a 95% confidence and a margin of error no greater than 3%. How large a random sample do we need? Okay, so here's the deal with that. The expression or the formula we use to figure out a confidence interval is this: P hat 1 minus P hat over. Okay, now here's the deal. This is the margin of error. Right there, that's the margin of error. So what we're trying to do is only work with that. We're not going to really care about the point estimate on its own. We care about the point estimate as part of the margin of error. What we're trying to do is we're trying to get that margin of error to be no greater than 3%. So we want it less than or equal to 3%. So what we want is we want this entire expression, Z hat, or Z star, P hat 1 minus P hat over N to be less than or equal to 3. Or 0.03, 3%. So here's the deal. It's going to be algebra. Here's the thing. We need to know pieces. So there are 3 unknowns there. I'm telling you, we're solving for sample size. So we're solving for N. So we need to know what Z star is and we need to know what P hat is. So the first thing I'm going to do is I'm going to look up in the problem and see if P hat is referenced in the problem at all. Since P hat is not referenced in the problem at all, what we use is the default proportion is 50%. The reason is 50% will give us the largest potential sample size that we need because when we multiply these two numbers together, when you multiply 0.5 times 0.5, you get 0.25 up top. That's the largest number. We want to keep that as large as possible. If you were to do other numbers, let's say 0.7 and 0.3 would give me 0.21 up top. That's a smaller number. So we're trying to make it as we're trying to get that number as big as possible. And the biggest difference in those proportions would be a 0.5. So we're going to use 0.5 as our best guess of the P hat. And we know Z star. We know Z star from the 95% confidence. We go to our table B. We go down to the infinity row of table B, and we're going to know that Z star is equal to 1.96. So now what we have is we have the following expression: 1.96 times the square root of 0.5 times 1 minus 0.5 divided by N is less than or equal to 0.03. And now it becomes an algebra problem. You got to solve for N. So the first thing I'm going to do is I'm going to divide both sides by 1.96. I'm trying to get that radical by itself. So I'm going to go ahead and divide 0.03. I'm going to divide it by 1.96. And that's going to give me 0.0153. So what that says is this radical thing here. I'm going to simplify that while I'm at it. That numerator is 0.5 times 1 minus 0.5. It's 0.25 over N is less than or equal to 0.0153. Well, now I need to free that up. So what I'm going to do is square both sides. And when I square 0.15, what I'm going to get is 0.25 over N is less than or equal to, and it's going to give me 2.34 e to the negative 4. So that's going to be 0.000. So it's going to be 0.00023. And now what I need to do is I need to free the N, multiply both sides by N. And what I'm going to end up with is 0.25 is less than or equal to 0.00023N. I'm just going to turn it around just because we're used to having the variable on the left side. So not less than, it's less than 0.25. And what I'm going to do now is to solve for N, I'm going to divide both sides 0.00023, 0.00023. So what I'm going to do is 0.25 divided by 0.12323. And that's going to give me N needs to be greater than or equal to 1086.96. And here's the deal. We are always rounding up. I know we would round up normally, but we're always going to round up. So in this case, I would need 1,087 people in my sample. It's honestly the most math you're going to do pretty much on any problem on the entire test, is trying to figure out the appropriate sample size. So that's how we do that. We're going to skip number 2 because that's means. I'm going to say it doesn't normally happen for means. I can show you it's the same process, but let's just stick with proportions for now. So now, college student, they want to figure out a margin of error of 4%. So again, what we're looking at is we're looking at this part of the confidence interval, p hat 1 minus p hat over n less than or equal to, in this case, our margin of error is 4%, so 0.04. Now, in this case, they give us a p hat, no problem. If we know the p hat, we're going to use that p hat. So we're going to replace this p hat with 0.75. Now, here's the deal, 90% confidence interval. If I go to table B and I look at the bottom of table B, here. That's it. No, don't have it handy. It's over on the other side. The Z star for 90% is 1.640. So 1.64, 0.75, 1 minus 0.75, divide by n, less than or equal to 0.04. And then I pick up the trusty calculator and I'm going to do the work in there. I'm going to do 0.04 divided by 1.64. 0.0244. So this is going to give me less than or equal to 0.0244. I'm just going to do the quick calculation here so I know what the numerator is. What I'm doing is I'm simplifying this guy up top. So 0.1875. So this becomes 0.1875 over n. I'm going to square both sides. So what I'm going to do is I'm going to go ahead and I'm going to square this number. So it's going to be 0.00059. So this is going to be 0.1875 over n is less than or equal to 0.1235. Multiply both sides by n. Just going to kind of jump a step on this. 0.159 is going to be greater than or equal to 0.1875. Divide both sides by 0.00059. So I'm going to go ahead and I'm going to do 0.1875 divided by that. And 315.19. So that's going to have to say 315.19. Now, again, this is where the always round up is. Even though technically in the world of math, if you were asked to round this to the nearest integer, it'd be 315, we always round up. So in this case, we're going to take 316 people. The reason we do that is because if we actually did this margin of error with 315 people, we'd end up with a margin of error that would be a little bit bigger than 4%. What I mean is this. So if I did 1.64 times, and what I'm doing is (1.64) times alpha y equals enter 0.75 times 0.25 over, and if I did 315 and I hit enter, it gives, sorry, I'm showing the screen. If I did this margin of error, 1.64, my 90% confidence, there's my numerator, my denominator, 315, I get a margin of error of 0.400119. Watch what happens when I change that number at the bottom to 316. So what I'm going to do is make this 316 instead. I get a number that's less than 4. So in this problem it says at most 4. That first one was not at most 4, it was over 4. So that's how we do sample sizes. So it comes up, it does come up at times, occasionally on free response, but usually it's a multiple choice question. Now here's the thing, bottom line, stop the sharing so I can make, bottom line is this. That's a lot of work, right? So here's the deal. A good kind of workaround is you take the answers they give you. So they're going to give you 5 different answers. And what I would do is I, guess and check. So take those sample sizes they give you, plug it into the given formula, calculate the margin of error and see how close it is to 4%. To add to that recommendation, I would always start with the middle number, because don't start with the lowest, because they usually have it from smallest sample size to largest sample size. So they'll be like, 50, 100, 150, 200, 250. I wouldn't start at 50, because if you're wrong on 50, you're going to go to the next one. You start in the middle at 150. If you are overshooting it, like let's say your margin of error is too large, you know that it's one of the 2 above it. If for some reason you are below it, you can then say, okay, now I only have 2 more to check. And what I would do is I would go and I would check maybe the last one. So I check 3, and then I check 5. And if 3 and 5, kind of get you around it, go and check 4. So I mean, like what I'm saying is don't go 1, 2, 3, 4, 5. Eliminate pieces if you can. So that's how you do sample size.